What are the key principles of classical physics that helps to revolutionize our understanding of work, energy, force, momentum, and matter? Is it possible that the current understanding of modern physics like relativity and quantum mechanics is possible without a good understanding of classical physics? What are the areas of continuous development that classical physics helps to modify and make great innovation in terms of technology, engineering, space, and even sending man to the moon? Well, in today's video, we are going to delve into a very serious and an important topic, why classical physics is important, and not only that, how the understanding of classical physics can help us to understand the modern physics, be it relativity, string theory, quantum mechanics, anything. My name is Shaunak and you're watching this video on my channel Physics for Students. Welcome to this video where we are going to look and delve deep into understanding classical physics and how and why it is important in making the understanding of modern physics much better. The basic objective of this video is not to teach you classical physics, which you already know by this time, but basically to look into classical physics in a different way. We would look into classical physics in a way that the deep underlying principles and understanding of classical physics, how it helps into understanding modern physics. We are also going to look through the different concepts of classical physics through which we can understand modern physics, quantum mechanics, relativity much better. Now hold on. You might be thinking with the advent of quantum physics and a new era which has revolutionized physics, mathematics and everything, we can just ignore classical physics and directly go into modern physics. Certainly not. And this is the objective of my video, to make you understand that how and why classical physics is so important. Without the knowledge of that, the entire understanding of modern physics is not done in a proper way. We either make mistakes or we hallucinate that we know physics. This video, first of all, what I would like to show you right on the screen is that what are the major domains of physics? As you can see, I have divided it basically into four areas: classical mechanics, relativistic mechanics, quantum mechanics, and quantum field theory. Now, when we talk of relativistic mechanics, let us make clear that relativistic mechanics, although it deals with Einstein relativity, it still falls under classical era and it is considered to be classical physics. Why? We will soon come to that. Now, when we talk of quantum mechanics, we will also see that although quantum mechanics deals with probability and probability distribution, uncertainty and various, I would say, counterintuitive phenomena, yet the basic root still lies in classical physics. I'm not going into quantum field theory, which is a totally different domain. So we will concentrate on relativistic mechanics and quantum physics, and thereby we will see and understand how the root of these are implanted in what we call is a classical field theory. By watching this video, you will also come to know that when you are learning modern physics at any point of time, if you feel that, okay, I am not able to understand these concepts, remember that you're not being able to understand not because of modern physics, not because that you don't know mathematics, because that you do not have a solid concept of classical physics. So I would advise, please go back, understand classical physics and then come back, because everything is ground rooted and implanted into the rules of classical physics. First of all, I would like to come to what is called a relativistic mechanics. Now, if I talk of relativistic mechanics, which started with the publication of Einstein's special theory of relativity in 1905, the first basic idea of making special theory invariant with the laws of physics is what? This one. Maxwell's equations should be made invariant along with the special theory of relativity. Again, you see, when we go back to Maxwell's equation, Gauss's law, electrodynamics, Faraday's law, all those things, these are basically what? Classical physics. I have made a different video. If you can go to my playlist in my channel Physics for Students, you will see that I have made a video, the history of classical mechanics to modern mechanics, where actually I have shown much more in detail that why special theory of relativity was basically based under the background of Maxwell's equation. And these Maxwell's equation, once they turn into relativistic equations, what do they actually mean? I'm not going into that. But here is a figure, illustration, as you can see right on the screen. The red box actually shows that these are the tensor formats of Maxwell's equations, which was quite going hand in glove, or we can say fitting hand in glove kind of a stuff with special theory of relativity. The 4 equations, which was originally written by Maxwell as 20 equation, was reduced by another physicist called Oliver Heaviside, who reduced this to 4 equations. So what I'm trying to tell in this part of the video is that going back to Maxwell's equation, which Einstein made relativistic, yet it made it classical, is because we need to understand Maxwell's equation. So point number 1, you see Maxwell's equation and the relativistic part of Maxwell's equation, which was done in special relativity, is implanted in classical physics. So here it shows that the root of special relativity is to make Maxwell's equation invariant. Now you might ask me a question, why? Because special relativity claims that the laws will be laws actually in a inertial frame of reference will behave in the same way whatever be the frames of reference. We know that Maxwell's equations deals with electromagnetism. So if electromagnetism and the constancy of the speed of light can be integrated into one specific theory, which is special theory of relativity, definitely it goes hand in hand. And this is the first reason that you see importance of classical mechanics. Until you understand Maxwell's equation very well, you won't be able to understand the relativistic part of Maxwell's equation. Whatever be the mathematics, whatever be the complexities, if you understand Maxwell's equation properly, then only the relativistic part will be clear. Point number 2, conservation of laws. Now you can see that conservation of laws, a conservation of mass energy or conservation of momentum, which we will see, these are also super important, because I will show you right now. You see that conservation of mass energy right on your screen shows that invariant mass and relativistic mass. So I would say the generalization which Einstein did in special theory of relativity, that there are 2 types of mass, right? One is an invariant mass, one would be a relativistic mass. Similarly, there are 2 types of energy. One is a rest energy, one is a relativistic energy. So all this, then there is a rest mass, there is a relativistic mass. You go to my video where I have shown this from classical to modern physics. I have also shown that why 4 momentum came from 3 vectors, because we need 4 dimension of space-time. So the 3 vectors came into 4 vectors. The reason is that until we understand the classical concept of philosophy of what is mass, what is energy, what is conservation, again you see the relativistic part, relativistic mass, energy, invariant mass, energy at zero energy, etc. These won't be clear. And that is the reason now you can see right on the screen E equal to mc squared, where the famous Einstein's equation where mass and energy were interchanged along with a multiple of the square of the speed of light, also comes from the basic root level, that is the concept of energy and mass in classical level. So right at this moment, what we saw is that the relativistic equations of Maxwell, the advent of 1905 special theory of relativity, and the conservation of mass and energy, which led to the famous E equal to mc square, was also derived, or the basic concept comes from classical physics. Now the question is that there is another thing which is called conservation of angular momentum. Obviously, it is a basic classical concept. Now you might question that, is it that conservation of angular momentum is not being extended to relativity or further? Here is the answer. Right on the screen you see conservation of angular momentum is also maintained in special theory of relativity as well as in black holes. As you understand that when the black holes swallow certain things, there is a very complex equation which shows that the angular momentum is being conserved. What does that mean? That means that if we extend the conservation of angular momentum directly into black holes and cosmology, we will see there also it comes from the basic grassroots level, that is classical angular momentum. So what is the message? The message is that until and unless you understand or thoroughly understand what is conservation of angular momentum, what is conservation of mass, what is conservation of energy, it won't be possible for any of us to extend it further and see those things into black holes or cosmology or even a special theory of relativity. I am taking a pause right now because like this there are numerous examples from classical mechanics Show you how and why classical physics and the concepts are very important. I'm not saying that you are ignoring classical physics, but it comes as a general because internet is plagued with a lot of modern scientific theories and quantum physics, etc., blogs, YouTube channels, etc. But remember that in order to know that, the basic ground truth level has to be absolutely certain and solid. Next part of modern physics, which is called quantum physics, which again has its root into classical physics. Let us consider this part. Right on the screen you can see it is called wave mechanics. Now, if you see that the wave-particle duality, the quantum superposition, the quantum entanglement, the double-slit experiment, the wave interferences, all these, even the imaginary number I, or the Euler's number or Euler's formula, all these are grass-rooted or implanted in the basic idea of wave mechanics. What is the message? What does it mean? It means that until and unless you understand the basic wave mechanics, that is the classical mechanics, be it the stationary wave, singular wave, be it the wave of a water, be it the sound wave, but everything has to be understood in a very proper and a complete manner. Because it is this particular concept of wave which is further being extrapolated as wave particle duality, and then the psi, that is a wave function, etc. We will come to wave function and wave particle duality much later. Until and unless we understand the concepts of the classical wave mechanics, until and we understand why it is exponential to the power I, theta, etc., then again suddenly if you start reading quantum mechanics, all these things becomes very weird, very bizarre, very complex, and we are unable to understand. So understand that wave mechanics is the basic essential, and again it shows the importance of classical physics. Here right on the screen you can see that the mechanics of the macroscopic world, what is happening is that right now I am sitting, there is a micro oven at the back, my books, my stores, my glasses, entire room is filled with things. Now if I start measuring the probabilities of those things which is on a macroscopic scale, we would lose out the probability density or amplitude that we calculate for an electron. But what happens in a quantum mechanical level, when we start identifying or measuring singular atomic or subatomic particles, we get into what we call probabilities, uncertainties, super probabilities reduces, and what we see is this: my body, your body, human beings, cars, toys, etc. That means that the macroscopic world actually is also full of probability, but that probability turns more sharper, more stronger when we move into the microscopic scale. So you see, this is basically again the classical mechanics taking over quantum mechanics when we are going to measure a particle or a single electron. So here, as I told you, combined together, the particles in the quantum world reduces the probability of the macroscopic world, quite certain. We come to the next part, which is called quantization. So the basic word quantum mechanics means what? It is that the energy levels are discrete. It cannot be continuous. Simple. But you see, again we go back to classical physics. Right here you see Bohr's atomic model, which shows that discrete energy level. That means a particular electron has to reside in a certain shell, and it cannot jump or take an abrupt or any kind of an abrupt number. It has to go from one shell to the second to the third, and it has got discrete jumps from one particular energy level to the second particle energy level. So if Max Planck's have discovered black body radiation, and then we went into quantization, then we went into photoelectric effect, and so on. But what is the root? Again, the root is Bohr's atomic model, where unconsciously it was discovered that the electrons or the subatomic particles actually take discrete energy levels. These discrete energy levels were further put as E equal to h nu and the Planck's constant, and we all know. Coming to the next part is what rules the quantum world, which is called Heisenberg's uncertainty principle. If you go back to my other video where I have made a very deeper understanding of uncertainty principle and Fourier transform, you will see that again the basic root is again classical physics, again classical concept. What is that Fourier transform? What is Fourier transform? I think I don't need to explain. So when we are trying to measure amplitude is either very dense, it is spread out, or it is very sharp. So if it is very sharp, we cannot get a particular position, we get a lot of amplitude. But again, when it is spread out, we get a lot of position, but not the amplitude. So again, the basic concept would be Fourier transform. And do is that you can just go and watch my video, which is called Uncertainty Principle and Fourier Transform, a deeper look into uncertainty principle. You will understand. The basic message is again, until and unless again we understand what is a Fourier transform, the basic underpinning philosophy of uncertainty principle won't be clear. We also come to the next part, which I would skip because it will take a long period. It is called Newtonian to Lagrangian and to Hamiltonian. What we are doing, we are taking the same energy level. Right on your screen you can see the Lagrangian denoted by L, and kinetic energy and potential energy is thus the difference. In case of Lagrangian and in case of a Hamiltonian, we are adding the potential and kinetic energy. This Hamiltonian again is being further extended as a Hamiltonian operator in quantum mechanics. Again, I've made a detailed video on what is called Hermitian and Hamiltonian operator. What does it mean? Go back and check it. Again, the message is simple, clear, that until and unless we understand energy, what is kinetic energy, what is potential energy, the extension to Lagrangian and is general theory of relativity of Einstein, you see force and space-time curvature. Simple. The Newtonian mechanics, that force is a gravity is a fictitious force, has been further extended to space-time curvature. Okay, now let me take a pause and make you understand a very, very important thing, which we will cover up in the next part of the video. The thing is that gravity, or general theory of relativity, again is a truly classical theory. What does it mean? That means it basically relies on Newton's law of gravity, and this gravity, which is considered as a force, has been extended through tensors and Einstein field equation as a curvature of space-time. But you see that when you are understanding or going deep into Einstein's field equation, which I have felt, and again I have to go back to classical mechanics, especially Newton's theory, Newton's laws of gravity, because the gravitational potential, the free particle, all these concepts are already being discussed by Isaac Newton and the classical mechanics. So the space-time curvature, which we see in the general relativity, again has its roots in classical mechanics. Number two, as you can see on the screen, motion and geodesics. So what is considered to be a direct motion in a straight line, where we use Euclidean or Cartesian coordinate to measure them, has been extended to geodesics, which is a straight line or the shortest possible path that a particle can take. But again, what is the root? The root is motion, straight line, the particle moving from one place to another. Gravity as a space-time curvature, I don't need to explain it further. This problem with understanding space-time curvature is basically we do not understand gravity well. Now, if you go to Leonard Suskind's famous lectures on gravity, general theory of relativity, way back all those 97, 98, those lectures, you will see that Professor Suskind has, explained a lot before coming to relativity, more about Gauss's law of gravity, Newton's theory, Kepler's law, etc. Why? The reason is that classical theory. So, if you want to understand space-time curvature, and I have seen it, seriously speaking, that's tensor. It is not because of any exotic or complex mathematics. It is because the basic concept of gravity is not clear. I mean to say the deep underlying understanding of gravity, until and unless it is not clear, it is impossible to go into relativity. I am saying that you know fairly good amount of mathematics. Remember, the mathematics of general relativity is not that complex. It is the problem that we do not. Right on your screen you see black holes are physics of classical gravity. Definitely. You may talk of Einstein's field equation when it is applicable, etc. I will come to that part much later, because Einstein's field equations are applicable under extreme circumstances. But when we observe a black hole, it is because it's bizarre or different kind of a behavior which has surrounding its stellar mass. That means the stellar objects which keeps on moving around. Also, I was just talking to one of my colleague, and he was telling that we often have the confusion that what happens when things fall inside a black hole. Falling inside a black hole will come for much later if we got an unstable orbit. But if it is a stable orbit, which is most common for all stellar composition, you will keep on moving and moving and moving around the orbit. It is not that you will fall. The energy will only be transferred when you have got an unstable orbit. So the problem is that the black hole physics, the metric, the Schwarzschild metric, it is not that difficult. It is difficult because again we do not understand the basic principles. I'm not talking of Newtonian, the general principle, the underlying principle, the basic philosophy, the deep-rooted, I would say, concepts of classical gravity. So as I have told, the observation of black holes are done as I told you right at the beginning, that the basic objective or the motto of this video is not to teach you classical mechanics, not to teach you Newtonian mechanics, but just to show you through these chronology of events, historical developments and the modern physics, how deeply it is rooted to classical physics. So you can again go back. All of us do go back to classical physics, Isaac Newton, Kepler, Maxwell's, Boltzmann, thermodynamics, etc. Because until that part is clear, we are unable to understand particle physics or modern physics. See, the problem is not with the exotic or complex mathematics of modern physics. The problem with us is that we do not understand. Your reaction by putting up a comment, and do not forget to subscribe to my channel Physics for Students. Click on the bell icon to get all the notification from Physics for Students, and soon I will be back with certain more interesting videos. Till then, goodbye.